those of you who don't know me, I'm Kaitlin Dennison, and I'm a fourth year PhD student in the Space Rendezvous Laboratory. And today I'm going to talk about how multi-agent stereo vision can be generalized to arbitrary targets in space. So here's my agenda for today. And first I'm going to go through the background and my motivations, and then I'll explain the sensitivity analysis that I've set up for these kinds of situations. I'll go through the results of that, and finally I'll show you some practical applications of this knowledge before I wrap up. So let's jump into the background and motives. So the main application I'm going to discuss today is non-cooperative target rendezvous in space. And this is a broad category that covers situations where any number of spacecraft might be approaching a target that cannot be actively communicated with, but the proximity is close enough that the resolved images of the target can actually be obtained. And this topic is growing a lot in popularity, especially for on-orbit servicing, rocket stage reuse, rocket refueling, and orbital debris recovery. It can also be extended to rendezvous with celestial bodies, such as comets and asteroids, where typically you'll have to analyze all sorts of characteristics, such as gravity coefficients and the entire shape model, along with doing some sort of autonomous navigation. And if you extend it all the way, you could really take this to terrain relative navigation, because technically it's a non-cooperative target when you're looking at the ground. And what these examples have in common is that their overall shape and pose of the target are generally partially or fully unknown. And target shape and pose knowledge are essential for safe guidance, navigation, rendezvous, proximity operations, etc. And while cameras are ubiquitously found on all types of spacecraft, they have a range ambiguity. And this presents a barrier to simply using the resolved images to obtain the target 3D model, because you have to use the relative geometries in order to obtain that range. So how is this range ambiguity solved today? There are two common approaches. The first on the left is LiDAR laser altimetry. And how this works is we fire a laser pulse at the target surface, and a detector waits and times how long it takes for that pulse to be reflected back into the emitter. And because we know the speed of light, we know exactly what that range is to some sort of uncertainty, but usually this measurement uncertainty is relatively constant, regardless of the actual range. And another method, which is what I'm going to be discussing today, is stereo vision. And this is often called triangulation. You'll hear me switch back and forth between the two. And here in this image, we have two cameras that are observing the same point P. And they both have a 2D measurement of this point in their images. If the camera positions in space are known, a ray can be traced from each camera through their respective 2D measurements, and the 3D point lies at the intersection of those two rays. So how do these two systems perform? Well, let's look at some data from the Hayabusa 2 mission to Ryugu. This mission had a static pointing LiDAR sensor, and I'm comparing it to a short-range camera built for space missions, the GOM Space NanoCam. And as you can see, the LiDAR system has a much higher power draw per measurement, about 18 watts. As a shorter range, it can only go up to about 25 kilometers from the surface before the laser altimeter can't really get a good reading on that pulse. And it's also a pointing only, unless you have something like a scanning LiDAR, which is, again, a lot more power draw, or a flash LiDAR, but the range is much, much smaller for a flash LiDAR system. However, when it comes to the camera, we're only pulling about 1.8 watts per image that's taken, and you can increase this range depending on your actual size of the target. In the case of Ryugu, which is about 1 kilometer in diameter, you can go about 40 kilometers before the target becomes too small to resolve anything. And the coverage becomes an entire image. And on the right, you can see results of a short simulation that I did, where it's comparing the actual LiDAR measurements from the Hayabusa 2 mission. So the red is the LiDAR tracks from the mission, and the blue are stereo vision point estimates that I did using sequential stereo vision from the same position tracks from the Hayabusa 2 mission. And this is where the LiDAR measurements are definitely superior to the stereo vision ones, because their precision is much higher. You get a meter to a half a meter uncertainty in them. Whereas the stereo vision estimates in this system, where I know the exact camera knowledge, you get about 4 meters of error in these estimates. And LiDAR is a de facto range recovery instrument used in space missions because it wins in precision. It's very simple, and it is lighting invariant, unlike the cameras. However, These are highly valuable attributes, but you get a lot of increased range, you get to significantly decrease your power draw, and there are a lot of other uses for cameras. So I believe that stereo vision is actually overlooked and underutilized in these kinds of spacecraft missions if you are willing to allow a little bit more uncertainty in your 3D measurements. Okay, so many researchers actually seek to increase the speed, accuracy, and precision of stereo vision in order to increase its usability. But I wanted to look at the user end and improve its simplicity, and thus decrease the barrier to entry for adding stereo vision to a mission's arsenal of tools that it can use. And there are a lot of interacting complexities in setting up these kinds of systems. So some questions that people would ask when they're setting up their mission design are, what kind of camera specifications do I need? Can I go with a really low resolution camera? How good does my camera actually need to be? Do I need to really account for noise, blurring, radial distortion, and things like that? Or can I just go with a really cheap off-the-shelf model? How close my spacecraft actually need to be to my target? And like I mentioned with the Ryugu, it depends on the size, and it's important to understand the differences when you have a different target. And how should I configure my distributed space system? So yeah, you can perform triangulation or stereo vision sequentially with a single spacecraft, but if you have a distributed system with multiple agents, like I'm going to be talking about today, you need to really understand how their relative positions influence the system. And again, what are my navigation requirements? Because the stereo vision depends on knowing those state positions of all of those agents. And how precise do my actual 2D measurements need to be, so the pixel measurements that I'm getting out of my images. And finally, what is the accuracy and precision that I can expect if I'm going to use stereo vision on this system? So it's useful to look at the mathematics behind stereo vision, as they'll be relevant later. And like I stated before, the 3D point is geometrically the intersection of two rays from the image frame. But in reality, there are errors that lead to this position of the rays not intersecting, or that intersection of rays being inaccurate. And so on the right here, I have the equations for computing the 3D point from my camera knowledge. So M is the camera projection matrix, and it's composed of K, which is the camera intrinsic matrix. This is composed of, spacecraft or the camera resolution and focal length. And R is the rotation from the arbitrary roll frame to the camera frame of reference, which has to do with your spacecraft attitude knowledge. And T is the translation from the camera center to the world frame origin. So the world frame is a completely arbitrary frame. It can be off anywhere and has nothing to do with your true 3D point. And the 2D so with this, my 2D measurements are simply the product of M and the 3D position P, is how you get that 2D point within the image frame. In an ideal world, the 2D point, lowercase p, is actually equal to m times p, and thus the cross product would actually be 0. And we exploit this and assume this to be true for both camera models. And through a little bit of linear algebra, you get this matrix, or this relationship, where it's a times p is equal to 0, where a is simply the camera projection matrix multiplied by the 2D points. And you can extend this to as many views as you want. You would just append new rows onto A as you get new camera perspectives. And this is quite easily solved through singular value decomposition because it's just a least squares problem. So the actual mathematics behind stereo vision seem quite complicated when you look at the diagram on the left, but in reality, it's something that we know how to solve very well and do all the time. And so like I said, researchers have focused on improving the speed, precision, and accuracy of stereo vision. And here's a quick history of methods that have been developed over time. The method I just explained to you is called the direct linear transform. It's quite basic, but performs surprisingly well in practice. Despite it actually being not projective invariant, this doesn't actually seem to crop up too much as an issue within the system. This system is often optimized using an iterative nonlinear optimization scheme. However, Hartley in 1997 developed the polynomial method that is provably optimal. So it is the absolute best case that you can get for a triangulation estimate. However, it can only be used within 2 views, and it's very computationally expensive to use. So all of the methods from that point on were focused on increasing the speed of the polynomial method, or they're focused on extrapolating that method to multiple views. And it wasn't until this year, earlier this year, that a method was developed that is usable under any number of views, and is actually much faster than the polynomial method with the same results. And all the results that I'm going to be showing you today are using an iterative nonlinear scheme, because that right now is the go-to method for multiple view stereo vision and triangulation. So let's move on to the sensitivity analysis that I performed to answer a lot of those design questions. So I decided to perform simulations of multi-agent stereo vision on two drastically different targets. So on the left, we have asteroid 433 Eros and the Tango spacecraft from the PRISMA mission on the right. And I would love to test my target on many different target types, but these two are quite different enough that if stereo vision characteristics can be generalized between them, there's hope that many other target types will also fit those generalizations. And just for some perspective, the maximum diameter of Eros is 33 kilometers, while Tango is about 1.5 meters in diameter. I also tested two different types of measurements across each of the simulation variables that I have on the left, and I'll go into those later, but let's look at these measurement types. The first are actual model vertices. You can't see them on the Eros one in the TV screen here, but they are there. And so these are simply the vertices of the triangular mesh model that I use to create these images. So I know their exact 3D positions, and therefore I can calculate the exact stereo vision error when using these. And the other one is I'm using SIFT key points on Eros and orb key points on Tango, because this is what we would realistically use in these kinds of missions. So now let's take a look at all these simulation variables. The first is the observer target geometry. Obviously, how many observers are we actually using to perform triangulation? Typically, as you increase the amount of data that you have about a topic, you increase the precision. And we want to see if that's actually true for this system. And on top of that, the spacecraft angular separation. Because as you decrease that angular separation, you actually increase the amount of error in triangulation, but I want to characterize what that actually looks like in this sort of system. And finally, we have target angular size. And this is so that I can generalize to any sort of system. So as you're very close to the target, your target angular size will increase drastically, and as you increase your distance to the target will obviously take up a lot less space within your image. And I want to know what are the differences in triangulation on these systems. And after that is the observer state knowledge. And this has a lot to do with how triangulation is actually performed, right? So observer state knowledge, whether it's absolute position error, which affects this t, the translation vector, or attitude error, which affects the rotation matrix r. This influences that camera projective matrix that is essential to determining the triangulation estimates. And measurement error is kind of the inverse issue, where it influences that the x and y positions that are going into your triangulation estimates. And on top of that is image corruption, and so this is things like Gaussian white noise or additive noise, blurring, radial distortion, and things like that. Okay, so let's look at a few of these results. And today this is the only result slides I'm going to show you, because I still need to perform some of the tests with the SIFT and orb measurements. So what you're looking at here are results of 4 of the different simulation variables for the model vertices of Tango and Eros. So Eros is the blue lines on these, and Tango is the red. And all of these, the left is the default parameters I have set while I am not, while I'm tuning each individual one of them. I have 5 pixels of noise error on the model vertices. I have a angular separation between the spacecraft and a target angular size of 20 degrees. And I'm also using 3 spacecraft. And what you see here, the y-axis of this is actually the residual as a percentage of the maximum width of your target. And when you account for the size of the target, these systems are actually extremely similar, which is very good. That means that my assumption that you could generalize between these two targets is probably true. And what you're actually looking at here is for the spacecraft angular separation and the target angular size, both of them around 20 degrees is about where any sort of benefit in increasing that number starts to drop off, where you really don't get any sort of benefit. And additionally, if I increase the number of spacecraft in these systems, you get a increase, or you get a decrease in that residual from 2 to 3 spacecraft, but anything after that is not actually a significant increase. So if you were to have a significant number of observers, you may not actually get a significant decrease in your residuals from triangulation. So the rest of these I'll come in later. So now let's look at some actual applications of this knowledge, right? And so this is a system that I have performed autonomous asteroid navigation and characterization. So in this system, we have data coming in from the sensors where we have 3 spacecraft observing an asteroid, where we have range, Doppler, and attitude solutions that come into my landmark tracking and stereo vision state. Like this, and then that provides stereo vision estimates and pixel measurements over to a state estimation filter, which is a UKF. And this UKF is performing navigation and target characterization, such as the shape model, gravity coefficients, etc. It's also keeping track of those landmark or stereo vision estimates over time and modifying them to keep up with the state estimates of all of the observers. And so this gets backtracked and put in again, where we're using the UKF built spacecraft state estimates in order to actually calculate the stereo vision estimates. And in this system, we found that an optimal solution for angular separation was about 12.7 degrees. So this is smaller than my 20-degree angular separation that I talked about before. But the reason for that is actually the SIFT drop-off. As you increase the separation between them, these images, like you're seeing right here, get more and more different, and these SIFT key point characteristics cannot keep up with that sort of perspective change. And here are the results of the actual system, where you're looking at the stereo vision error over here. This entire system had a stereo vision error of about 12 meters, which is extremely good considering the size of errors is 33 kilometers. And you can see that the navigation is actually able to perform extremely well just using these stereo vision estimates and the 2D pixel coordinates. And over time, the system is able to develop a full 3D model that uses all of those landmarks that were generated over the system. And this is another slide I need to finish, but the other application is for non-cooperative spacecraft pose estimation, where you can utilize stereo vision in order to track and estimate the spacecraft pose over time. And I hope to incorporate this with Jeff's CNN for his pose estimation and hopefully help him kickstart that for cases where there is no shape model available a priori. Okay, so let's look at the main takeaways of the system. Well, there's a lot of applications that you can use multi-agent stereo vision for. And I truly believe that this type of data is underutilized because you get a lot of benefits from simply having a camera as opposed to using a full LiDAR system where it's a single-use sensor. And performance in these systems can be generalized to a single target, an arbitrary single target, based on characteristics such as target size and the camera specifications. And like I said, increasing angular separation and size has diminishing returns after 20 degrees. And increasing the number of spacecraft doesn't actually significantly improve performance much after 304 agents. And also, this performance is accurate enough to support autonomous navigation and characterization of an asteroid, which is extremely important because that would be one of the main applications. And for my future endeavors, I hope to extend this analysis to include structure from motion, where not only am I recovering the structure or the 3D points of a target, I want to actually perform navigation and recover the position and attitude of the cameras themselves and remove that assumption that you need to have that spacecraft state knowledge. And also look at spacecraft relative position error as opposed to absolute position error. Include time synchronization, which is often overlooked in these kinds of systems, because if I'm using multi-agent stereo vision, we need to make sure that those images are entirely time synchronized, otherwise your data can be significantly inaccurate. And target motion has a lot to do with that kind of system. And then also, if I can, extend this to real images.